Now we are going to study about atomic spectra. When a metallic body is heated, it emits electromagnetic radiations having different wavelength. It consists of different components of radiations having different wavelength. For example, when the filament of an electric bulb is heated, it emits white light consisting of radiations in the visible range. When this white light is passed through prism, we obtain the continuous spectrum consisting of all the wavelength in the spectrum. This spectrum appears as bright lines. Similarly, when hydrogen gas is heated at a high temperature, it emits radiations. When these radiations passed through a prism, we obtain hydrogen spectrum. This spectrum is not a continuous spectrum. It consists of shortly defined discrete wavelengths. When an atomic gas or vapor is excited at a low pressure, usually by passing an electric current through it, the emitted radiation has a spectrum which contains certain specific wavelengths only. A spectrum of this kind is termed as emission line spectrum, and it consists of bright lines on a dark background. The line spectrum is characterized by elements emitting it. This means no two elements can give the same line spectrum, so it is called fingerprint spectrum. Spectral lines are grouped into several spectral series are shown in the figure. When white light is passed through a gas and when we analyze the transmitted light, we get a spectrum called absorption spectrum. The absorption spectrum consists of dark lines corresponding to wavelength which were found in the emission line spectrum of the same gas. Figure shows the emission line spectrum of hydrogen atom. It consists of bright lines on a dark background. Hydrogen is the simplest atom and therefore it has the simplest spectrum. In this absurd spectrum, at first sight, there does not seem to be any resemblance of order or regularity in spectral lines. But the spacing between the lines within certain sets of the hydrogen spectrum decreases in a regular way. Each of these sets is called spectral series. So here some of the spectral series are shown in the figure, and here the spacing between the lines decreases in a regular way. The first spectral series was observed by Johann Jacob Balmer in 1885, a Swedish school teacher. This Balmer series is in the visible region of hydrogen spectrum, and this is the schematic representation of the Balmer series. When you observe here, the spectral lines or the spacing between the spectral lines decreases in a regular interval. The first line in the Balmer series is known as the H alpha line. It is the longest wavelength and it has the wavelength of 656.3 nanometer, and it is in the red region of the visible region. Then the second line is known as the H beta line, and it is in the blue-green region, and it has the wavelength 486.1 nanometer. The third line is known as the H gamma line, and it is in the violet region, and it has the wavelength 434.1 nanometer. And then H delta line, and so on. And finally, the shortest wavelength in the Balmer series is known as H infinity, and it has the wavelength 364.6 nanometer. When the wavelength decreases, then the lines appear closer together and the intensity of the spectral lines also become weaker. Balmer found an empirical formula to calculate the wavelength of spectral lines, that is 1 by lambda equal to r into 1 by 2 square minus 1 by n square, where r is the Rydberg constant. Its value is 1.097 into 10 raised to 7 meter raised to minus 1. 2 represents that Balmer series is the second series in the emission spectrum of hydrogen atom, and n has the integral values 3, 4, 5, etc. By taking n equal to 3, by substituting in the formula, we get the wavelength of H alpha line, that is lambda equal to 656.3 nanometer. It is the longest wavelength in the Balmer series. And when you substitute n equal to 4, we get the wavelength of H beta line. And n equal to infinity, we get the wavelength of shortest wave, that is lambda equal to 364.6 nanometer. It is the shortest wavelength in the Balmer series. Similarly, the first series is Lyman series, third series Paschen series, fourth series Brackett series, fifth series Fun series. For the Lyman series, the formula to calculate the wavelength of spectral lines is 1 by lambda equal to r into 1 by 1 square minus 1 by n square, where n equal to 2, 3, 4, etc. 1 represents that Lyman series is the first series and it lies in the ultraviolet region of the emission spectrum. Then the third series, Paschen series, its formula is 1 by lambda equal to r into 1 by 3 square minus 1 by n square, where n equal to 4, 5, 6, etc. 3 represents that it is the Paschen series is the third series. Then Brackett series, formula is 1 by lambda equal to r into 1 by 4 square minus 1 by n square, where n equal to 5, 6, 7, etc. 4 represents that Brackett series is the fourth series. Then Fun series, 1 by lambda equal to r into 1 by 5 square minus 1 by n square, where n equal to 6, 7, 8, etc. 5 represents that Fun series is the fifth series. All these series are represented after the discoverer. Then this Paschen series, Brackett series, Fun series lies in the infrared region of the emission spectrum. Then also we can calculate the frequency of these spectral lines. You know that C equal to nu lambda, where 1 by lambda equal to nu by C, and you can substitute this 1 by lambda in the above equations. So nu by C equal to r into 1 by 2 square minus 1 by n square, where nu frequency nu equal to rc into 1 by 2 square minus 1 by n square. This is the formula to calculate the frequency of the spectral lines in the Balmer series. So we can see the emission lines spectrum of the hydrogen atom. So these are the different series, that is first series Lyman series, second series Balmer series, third series Paschen series, and so on. In all these series, the spectral lines are arranged in the spacing between the spectral lines are arranged in a decreasing order, and when the wavelength decreases, the lines becomes closer together and it has the weaker in intensity. Thank you.